Right now, the most advanced, weightless, magical software humanity has ever created,
Oh, yeah.
artificial intelligence. It is completely dependent on the heaviest, dirtiest, most industrial objects on Earth.
It really is.
I mean, we are talking about 300-ton steel transformers, high voltage power grids, hundreds of miles of copper cabling, and literally liquid-cooled fortresses.
Fortresses is the right word.
Yeah. So today we are dragging the cloud back down to Earth.
It is a massive physical reality check.
Mm.
For the last 2 decades, software has conditioned us to believe that technological progress is, well, ethereal.
Right. Invisible.
Exactly. You write some code, you push an update, and suddenly a billion devices have a new feature. But the AI revolution, it just doesn't work like that.
No.
It is the absolute definition of an industrial mega project.
Yeah.
I mean, we are looking at the most resource-intensive physical build-out since, honestly, the electrification of the world.
And that is exactly what we are dissecting today. So, welcome to the deep dive, where we take a stack of really dense, intimidating source material and extract the absolute most important insights just for you.
Yeah, doing the heavy lifting.
Exactly. So our roadmap for this journey is the Q4 FY26 investor update from Exponent Tribe LLP. And our mission today is to completely demystify what they call the AI infrastructure opportunity.
Right, moving way past the chatbots.
Way past the hype. Because if you want to understand how this technology actually works and where literally trillions of dollars are flowing, you have to look at the cables.
The industrial coolants.
Yes, and the power plants. Okay, let's unpack this.
It really is the only way to truly grasp the scale of what is happening. Because when you say the cloud, or when you use an AI assistant on your phone, you're actually triggering a physical machine sitting inside a physical building somewhere.
Right. There is no magic cloud. It's just someone else's very hot computer.
Exactly. And what Exponent Truck does brilliantly in this letter is they force us out of our software-induced complacency. They lay out the just unyielding laws of physics and economics that are currently governing human progress.
But before we get to the steel and the power lines and all the heavy stuff, let's establish why this frantic build-out is even happening.
We have to start with the capability shift.
Right. You probably remember the explosive launch of ChatGPT back in November 2022. The user adoption numbers were just staggering.
Mind-bending.
It hit 100 million users in 2 months. And to put that into perspective for you, Netflix took 120 months to hit 100 million.
Wow.
Twitter took 60 months. Even a viral sensation like TikTok took 9 months.
Right.
ChatGPT did it in 8 weeks.
And, that wasn't just a flash in the pan. The novelty didn't wear off. Here we are in April 2026, and the report cites 900 million weekly active users.
900 million.
Think about the gravity of that number. Roughly 1 in 8 human beings on planet Earth are interacting with this system every single week.
It's a level of penetration that honestly defies historical comparison. But honestly, the user numbers are almost secondary to the actual utility being unlocked.
Oh, absolutely.
We aren't just talking about a highly efficient search engine anymore. We are talking about a general-purpose reasoning engine.
Yeah.
You have a system that can, debug complex Python code, analyze a dense 10K financial statement, draft a watertight legal brief, and summarize niche medical research.
All in the span of 5 minutes.
Exactly.
And that general utility is what changed the world. Every single generation of these frontier models expands the boundary of the possible. I mean, software engineers are deploying production-ready code in 3 hours that would have historically taken a team 3 weeks.
Which brings us to an incredibly poignant story from the Exponent Tribe update. And I think this perfectly illustrates the shift for you guys listening.
It's a great example.
So in March 2026, an Australian data engineer named Paul Cunningham received devastating news. His dog, Rosie, was diagnosed with cancer and given just months to live.
It's a terrible situation. It forces people into very desperate corners.
But Paul's response is what illustrates this capability shift perfectly. He didn't just accept the prognosis. Paul utilized ChatGPT alongside Google DeepMind's AlphaFold.
Right.
Now, for those who might not know, AlphaFold is an AI system that solves one of the hardest problems in biology, predicting the 3D structure of a protein from its amino acid sequence.
Which is incredibly complex.
Exactly. So Paul used these tools to help design a personalized mRNA cancer vaccine specifically tailored to Rosie's tumor. He collaborated with researchers at the University of New South Wales.
Yeah.
And they went from a physical tumor biopsy to a manufactured personalized vaccine in under 2 months. The primary tumor shrank by roughly 75%.
Now, We have to be very careful here.
Oh, for sure.
And the source makes this explicit. This is an anecdotal case. It is a single data point.
Right, it's not a double-blind clinical trial.
Exactly. Oncologists rightly caution against drawing sweeping medical conclusions that cancer has been broadly cured.
Sure, the medical anomaly itself isn't really the primary takeaway. The takeaway is the access.
Precisely. The point is the capability shift. I want you to really think about what was required to do something like that just 5 or 10 years ago.
It would be impossible for one person.
Completely. Yesterday's cutting-edge biomedical breakthroughs required hundreds of millions of dollars in R&D investment. You needed physical laboratories packed with mass spectrometers, vast specialist teams holding multiple PhDs.
Decades of institutional trial and error.
Exactly.
And what did Paul have?
Yeah.
He had a consumer-grade laptop, an internet connection, and just absolute sheer persistence.
That is the paradigm shift. The capability to design candidate therapies, a power that used to sit exclusively behind massive institutional walls, is now accessible to a highly motivated guy sitting in his living room.
It's unbelievable.
The bottleneck to innovation is no longer strictly human intelligence or decades of specialized training or massive institutional capital.
Okay, I hear you, but let me push back a little here. The bottleneck has shifted, yeah, but my laptop didn't suddenly become a supercomputer overnight.
Right.
The MacBook sitting on Paul's desk isn't physically capable of simulating billions of protein folding combinations.
No, of course not.
So if the capability is accessible from a laptop, what is actually doing the heavy lifting?
That is the crucial question, and it is the bridge from the software illusion to the physical reality. Your laptop is basically just a walkie-talkie.
Oh, walkie-talkie.
Yeah. Every time you ask ChatGPT to rewrite an email, or Paul runs an AlphaFold simulation, your device sends a signal to a physical machine in a physical building. That machine performs the actual computational heavy lifting.
And sends the answer back to your screen.
Exactly.
The data center.
Yes, the data center. A facility specifically built to house massive amounts of computing hardware, deliver the astronomical amounts of electricity required to run it, and remove the intense heat it generates.
Now, data centers aren't new. I mean, the internet has run on them for decades.
Sure.
Your banking app, your streaming video, your social media, they all live in data centers.
Right. But the old data centers and the new AI factories are fundamentally different beasts, and the difference comes down entirely to the silicon chips inside them.
Okay, let's break that down, because this is where the physics of the situation starts to dictate the economics. The report draws a very sharp line between CPUs and GPUs.
Yeah.
For basically the entire history of modern computing, the standard was the CPU, the central processing unit.
The CPU is a marvel of engineering, truly, but it is a general-purpose processor. It is designed to handle a wide variety of tasks sequentially.
One after the other.
Exactly. Think about what a web server does. It loads an image, then it processes a secure payment, then it looks up a record in a database. It jumps from task to task.
Highly varied work.
Right. It requires complex logic branching, but none of it requires massive parallel mathematical computation.
I always think of a CPU like an incredibly fast, highly educated executive assistant.
Okay, I like that.
You can give them 100 totally different tasks. Book a flight, draft a memo, balance a spreadsheet, and they will do them all perfectly, one after the other. But they are just one person.
It's a solid mental model. Now, when a company says they're building an AI model, what they're actually doing is taking unimaginable quantities of data.
Like the entire text of the public internet.
Exactly. Millions of images, billions of lines of code, and feeding it through tens of thousands of GPUs, or graphics processing units.
So if a CPU is the executive assistant doing complex tasks one by one, what is the GPU doing differently?
GPU does not handle varied tasks well at all. It is terrible at logic branching. Instead, a GPU runs trillions of incredibly simple mathematical operations simultaneously.
At the exact same time.
Right. It does this over and over again for weeks or months, adjusting the internal weights of the software until the system learns to predict the next word in a sentence or the next pixel in an image.
So instead of an executive assistant, a GPU is more like an entire stadium full of high school students who only know basic arithmetic.
That is a brilliant way to picture it.
Right. If you need to multiply a million different numbers by 2, the executive assistant would take forever doing it one by one. But you hand one number to each student in the stadium.
They all multiply by 2 at the exact same moment.
And you get your answer instantly.
Yes, massive parallel processing. And unlike the CPU, which handles a web request and then effectively rests for a fraction of a second, an AI GPU running a training workload Flat out does not rest.
No breaks.
None. It runs at near 100% utilization, around the clock.
And this is where the physical consequences kick in. Because you have a chip running thousands of calculations simultaneously without stopping, it draws a terrifying amount of electricity.
It's massive.
The report notes that the latest AI chips draw 5 to 10 times more power than a traditional CPU, occupying the exact same physical space in a server rack.
5 to 10 times more power in the same physical footprint. That is a thermal density nightmare. An older, traditional data center full of CPUs is essentially like a large, modern office building. It has a moderate electrical load, and it uses standard, heavy-duty commercial air conditioning to keep the ambient temperature cool.
But an AI data center full of GPUs...
It's not an office building. The engineering required makes it much closer to an aluminum smelter.
An aluminum smelter,
It's-
that implies extreme, dangerous levels of concentrated energy.
It requires industrial-grade power infrastructure and specialized liquid cooling systems just to prevent the building from catching fire.
Wow.
And the cost to build these facilities scales directly with the physics. A standard cloud data center costs roughly $8 million to $10 million per megawatt of power capacity to construct.
Okay.
An AI-optimized facility. That jumps to $15 million to $20 million per megawatt.
Double the capital cost just for the building and the electrical guts.
Easily double.
But before we actually tour one of these facilities, we need to understand the two different modes of operation for these GPUs, because the report highlights two distinct forces driving this compute demand: training and inference.
And if you don't understand the difference between training and inference, you literally can't understand the infrastructure boom.
Right. Let's define them.
Training is the brute force process of actually creating the AI model from scratch. It is that period of weeks or months of continuous computation we just discussed.
So when OpenAI decides to build the next generation of ChatGPT, like GPT-5, they are entering a training run.
Yes. And it happens once per model generation. It's highly concentrated, enormously expensive, and it requires tens of thousands of GPUs to sit in extremely close physical proximity to one another.
Why proximity? Why do they have to be close?
Because during training, the GPUs are constantly exchanging massive amounts of intermediate data. If they are far apart, the time it takes for data to travel across a network cable slows the whole process down.
I see.
That's why training data centers are usually massive, monolithic campuses located in remote areas where land and electricity are cheap and abundant.
Okay, so training is the multi-month heavy lift to build the brain. It's the R&D phase. Once the brain is built and released to the public, what is inference?
Inference is the application of that brain. When you type a prompt into ChatGPT, or when you ask an AI tool to summarize a PDF, the system runs your query through that already trained model to generate an answer.
It infers the answer.
Exactly. That single action, predicting the output based on the input, is an inference operation.
So training builds the system, inference uses the system.
Exactly. And the economics of inference are fundamentally different. While a single inference operation requires a fraction of the compute power compared to a full training run, it happens continuously.
Because people are always using it.
Right. It scales directly with user adoption, and it never, ever stops. If a model is fielding 1 billion queries a day globally, that infrastructure is performing 1 billion inference operations every single day.
And the growth metrics in the report for inference demand are just staggering. Between April 2024 and October 2025, so just an 18-month window,
Very short time.
the number of tokens processed per month across Google's AI surfaces went from 9.7 trillion to 1,300 trillion tokens.
Let's clarify what a token is for a moment for those who don't know.
Good idea.
In AI, a token is roughly equivalent to a word or a piece of a word. When an AI generates a 500-word essay for you, it is computing and outputting roughly 600 or 700 tokens.
Okay.
Generating 1,300 trillion tokens per month requires an unbelievable fleet of GPUs doing nothing but inference work.
It's a compounding, steady demand. It's not a one-off burst. You look at a company like Anthropic. The report notes their annualized revenue grew from $1 billion in 2024 to $30 billion by March 2026.
Huge jump.
And if you are generating $30 billion by selling AI access, every single one of those dollars requires physical compute infrastructure to deliver the inference. You can't fake it with clever software.
You cannot fake the physics. Every token generated burns real electricity and requires real silicon.
Which catapults us into Section 3, the trillion-dollar arms race.
Oh, this is where the numbers get crazy.
Because these hyperscale tech companies need these aluminum smelters of data for both training the next frontier model and serving inference to a billion users, they are locked in a spending cycle that just defies traditional corporate logic.
The capital expenditure numbers in the first section of the update are difficult to even comprehend. We are looking at the 5 hyperscalers: Amazon, Microsoft, Alphabet, Meta, and Oracle.
The giants.
These are the engines of the modern internet.
So in 2024, those 5 companies spent a combined $257 billion on capital expenditures.
$250 billion.
And then in 2025, that figure jumped 73% to roughly $440 billion.
And it doesn't stop there.
No, looking at the guidance for 2026, they are projecting a combined capital expenditure of $685 billion.
Let's pause on that. $685 billion in 1 year.
That is higher than the gross domestic product of many developed nations.
Easily. And the report includes a chart showing capital expenditure as a percentage of revenue.
Right.
If you look at normal capital-intensive industries, like telecommunications or traditional manufacturing, if CapEx hits 15 to 20% of revenue, Wall Street analysts usually start getting very nervous.
Because it means you are reinvesting a massive chunk of every dollar you make just to keep the lights on and grow slightly.
Exactly. But look at the hyperscalers' projections for 2026. Amazon is dedicating 25% of its revenue to CapEx.
Okay, high.
Alphabet is at 46%. Microsoft is at 47%. Meta has more than doubled its capital intensity in just 3 years, hitting 54%.
And then you look at Oracle. This one blew my mind.
Yeah, Oracle is wild.
Oracle is projecting to spend 86 cents of every single revenue dollar they make on capital expenditure. 86%.
That's unprecedented.
If you are an investor looking at this, your first instinct has to be, this is a bubble. This is highly irrational behavior. Why don't these 5 CEOs just get in a room, mutually agree that this is out of control, and tap the brakes?
They can't tap the brakes.
Why not?
The report explains exactly why, using 2 core frameworks: game theory and scaling laws.
Okay, game theory. The classic prisoner's dilemma. Meaning, if I stop spending and my competitor doesn't, I'm dead.
It is an asymmetric risk profile. Think about it. If Alphabet overinvests by $50 billion and AI adoption slows down, what happens? They waste some capital.
Right.
Their margins compress, their stock takes a hit, but the company survives. They are fine.
They have the cash.
However, if Alphabet underinvests by $50 billion and OpenAI or Meta successfully trains a model that is a full generation smarter.
Oh, I see. Alphabet's core product, Google Search, becomes obsolete.
Overnight. A generation behind on compute means you are a generation behind on intelligence. And if your competitor has a smarter AI, users will migrate instantly.
Wow.
So it is literally an existential arms race.
But what guarantees that spending $50 billion actually yields a smarter AI? That's where the scaling laws come in, right?
Exactly. In artificial intelligence research, a scaling law is the empirically observed relationship that dictates performance.
And it's proven.
It is a proven mathematical pattern validated across billions of dollars of spending over the last decade. It shows that if you train a neural network architecture on vastly more data, using vastly more computing power, the resulting model produces measurably better, more generalized reasoning capabilities.
So it's not a theoretical hope, it's a predictable curve. The more compute you feed the training run, the lower the loss function, meaning the fewer errors the model makes.
Right. And because that law holds true, the cost of training frontier models has just exploded. The report charts this beautifully.
Yeah, let's walk through those numbers.
Back in 2020, OpenAI trained GPT-3. The compute cost was roughly $4 million.
Okay, reasonable for a tech giant.
By 2023, the compute cost to train GPT-4 was estimated at $80 million.
A big jump.
In 2024, Meta's Llama 3 cost roughly $170 million.
Okay.
And for the projected frontier models in development for late 2025 and 2026, they require $1 billion to $2 billion in dedicated compute time just for a single training run.
$1 billion just to run the software through the chips for a few months.
Just for the compute time. Because the scaling laws dictate that more compute equals a better model, these companies absolutely must spend the money, or they voluntarily surrender the future to their competitors.
This relentless pressure is why global AI compute capacity is doubling every 7 months. By late 2025, the world had an estimated 15.7 million H100 equivalent GPUs installed.
That represents a 50 times increase in global compute capacity in less than 4 years.
And it is so intense that the traditional tech giants aren't even the only players anymore. The report highlights the rise of these so-called neoclouds.
Neoclouds are fascinating. These are companies like CoreWeave, Nebius, and Lambda.
5 years ago, they barely existed in any meaningful corporate sense.
Right, but today they are building AI-specific data centers from the ground up, optimized purely for massive GPU clusters.
Yeah.
They don't mess around with general-purpose CPU cloud hosting.
CoreWeave alone is expecting to spend $30 billion to $35 billion in CapEx in 2026. And they already have a $55 billion revenue backlog.
It's wild. Microsoft is so desperate for compute that they actually committed $60 billion over several years to these neoclouds because Microsoft physically cannot secure land, permits, and power fast enough to build their own data centers.
Which highlights a fascinating financial reality. Historically, these hyperscalers are the most cash-rich, profitable companies in the history of global capitalism.
Sure.
They generate tens of billions in free cash flow every quarter. But even their colossal cash hoards are not enough to fund this build-out.
No, they're turning to the debt markets to bridge the gap.
The report mentions the tech sector might need to issue as much as $1.5 trillion in new debt over the next few years just to pay for the concrete, copper, and chips.
They're leveraging up to secure physical infrastructure because the constraint is no longer software talent or internal cash.
It's the physical world.
Exactly. The constraint is physical reality. It's the time required to secure a massive plot of land, get an interconnection agreement with the local power grid, and physically pour the concrete.
So we have hundreds of billions of dollars leveraged by debt flowing into physical infrastructure. If you are an investor or just someone trying to understand where the world is going, you need to know exactly what $1 billion buys you.
Yes.
And that brings us to Section 4. The report takes us on a highly detailed physical walking tour of a modern 100-megawatt AI data center. They deconstruct this multi-billion-dollar asset into 5 distinct layers.
This is where the abstract, ethereal concept of the cloud becomes very, very tangible.
Let's set the baseline. A state-of-the-art 100-megawatt AI data center costs approximately $3 billion to $3.5 billion to construct.
And the most shocking part to many people is that roughly half of that cost, around $1.5 billion, is spent before you even purchase a single AI processor.
Wow.
It is entirely dedicated to the physical building and the non-IT infrastructure.
You spend $1.5 billion on concrete, steel, pipes, and wires.
Basically, yes.
Let's start at layer 1, power supply and generation. You called it an aluminum smelter earlier. How much power are we really talking about?
A 100-megawatt facility draws a continuous electrical load, roughly equivalent to a town of 70,000 to 100,000 people.
A whole town.
And unlike a town where power usage drops at night when people go to sleep, an AI data center runs at maximum load 24 hours a day, 365 days a year.
The electricity bill alone is projected at $80 million to $130 million a year, just to pay the utility company.
And getting that much power off the public grid and into the facility is a massive engineering undertaking. You don't just plug this into a wall.
No, obviously not.
High voltage power, typically anywhere from 66 kilovolts up to 220 kilovolts, is routed from the grid transmission lines to a dedicated massive electrical substation built right next to the data center.
And that substation alone, just the facility to receive the power, costs $50 million to $70 million.
Yes. It is filled with incoming high-voltage feeders, complex protection relays to prevent grid surges, medium-voltage switchgear, and the massive step-down transformers.
But because the public grids in many countries are becoming entirely saturated, data center developers are increasingly realizing they can't rely on the public utilities.
They can't wait for them.
So they are moving to behind-the-meter generation.
Right.
Meaning they are just building their own power plants right next to the server farm.
Exactly. The report specifically mentions CCGTs, combined cycle gas turbines.
Let's explain how those work, because it's a brilliant piece of thermodynamic engineering, and it highlights a specific Indian company benefiting from it.
A standard gas turbine burns natural gas to spin a generator, much like a jet engine. But it exhausts a massive amount of incredibly hot gas as waste.
Right.
A combined cycle system captures that extremely hot exhaust gas, routes it through a heat recovery steam generator to boil water, and uses that high-pressure steam to spin a second, entirely separate steam turbine.
So you get 2 distinct phases of electricity generation from the exact same unit of fuel. You burn the gas to spin a turbine, and you use the waste heat to boil water to spin a second turbine.
It radically increases the thermal efficiency of the power plant, which is absolutely vital when you are consuming 100 megawatts constantly.
And the report highlights an Indian precision engineering firm, MTR Technologies, which manufactures highly complex, tight tolerance components for these exact turbine systems.
Yeah.
As global demand for behind-the-meter data center power skyrockets, the demand for these precision turbine components scales directly with it.
And the report also points out that the hyperscalers, Google, Microsoft, Meta, they have massive corporate sustainability commitments.
True, they can't just burn natural gas everywhere.
So they are heavily funding renewable power. They call out CleanMax Solar. Their data center segment has grown 10 times over in less than 2 years.
They are guiding for 1.5 gigawatts of new renewable capacity in the next fiscal year, primarily driven by data center power purchase agreements.
So that covers layer one, actually generating the raw megawatts and getting them to the edge of the property line. But that brings us to layer two, which is power distribution and reliability. Once the high voltage power reaches the substation, it has to travel through an incredibly complex, meticulously engineered chain to reach every individual silicon chip in the building.
And it has to do this with absolute perfection.
Perfection is not an exaggeration. The report notes the industry standard for data center uptime is 99.999%.
5 nines.
Yes. If you do the math on a year, 5 nines of reliability allows for roughly 5 minutes of unplanned downtime per year.
And in an AI training context, even 5 minutes is catastrophic.
Oh, completely. If you have a cluster of 50,000 GPUs working on a unified mathematical problem for 3 weeks, and the power dips for even a fraction of a second, the entire cluster faults.
You can corrupt days of computational work, wasting millions of dollars in electricity and lost time.
To achieve 5 nines of reliability, every single critical component in the power distribution chain has to be doubled or sometimes tripled for redundancy.
Let's walk through that chain because this is where we hit one of the most severe supply bottlenecks on the planet. The power hits the main substation at up to 220 kilovolts. The servers inside the building obviously cannot take 220,000 volts.
They'd explode.
So it has to go through step-down transformers.
A 100-megawatt facility needs anywhere from 8 to 12 of these primary medium voltage transformers. And these are not off-the-shelf products you buy from a catalog.
A single large power transformer costs between $2 million and $5 million.
And the report quotes a Taiwanese manufacturer regarding the lead times for these transformers. If you want a transformer right now, the wait time is 2.5 to 3 years.
2.5 to 3 years.
If you need it in 18 months, you physically cannot buy one for any amount of money. The capacity does not exist.
Why on earth are these things so hard to build? Why can't we just spin up an assembly line and turn them out like cars?
Because building a high-voltage transformer is much closer to artisanal watchmaking than it is to automotive assembly.
Watchmaking.
It requires extreme precision with massive, heavy materials. Let's look at the physics. A transformer works on Faraday's law of induction. You run high-voltage electricity through a massive coil of copper wire.
Okay.
That creates a fluctuating magnetic field. That magnetic field then passes through a steel core and induces a lower voltage current in a second, separate copper coil.
So the electricity doesn't actually touch. The energy is transferred purely via the magnetic field passing through the steel core.
Exactly. But if you just use a regular block of steel for the core, the change in magnetic field creates massive internal eddy currents.
Eddy currents.
Yeah, the steel heats up intensely, you lose a ton of energy to heat, and the transformer melts down. So they have to use a highly specialized material called grain-oriented electrical steel, or GOES.
Grain-oriented, meaning they physically alter the atomic structure of the steel?
Yes. During the metallurgical process, the silicon steel alloy is rolled and heat-treated in such a way that the crystal structures of the metal are literally aligned in one specific direction.
Wow.
This allows the magnetic flux to slip through the steel with almost zero friction or energy loss.
That's incredible. So you are taking atomic-level precision steel, winding tons of highly pure copper wire around it completely by hand.
By hand, because machines can't wind it tightly enough without breaking the insulation.
And then you seal the entire 300-ton apparatus in a welded tank filled with specialized insulating oil.
And you cap it with custom-engineered ceramic bushings to safely carry the high-voltage current through the steel casing without creating an arc flash.
It's a massive process.
The specialized labor, the materials, and the testing facilities required to build these mean you can't just open a new factory overnight. It is a massive global bottleneck.
And the report highlights an Indian player brilliantly capitalizing on this exact constraint, CG Power and Industrial Solutions. They just secured a massive $99 million export contract for a U.S. data center project specifically to supply 330 kilovolt power transformers. Because the U.S. domestic supply chain is entirely maxed out, American developers are looking globally.
CG Power is expanding their transformer manufacturing capacity by 40% right now, just to address this export demand.
It perfectly illustrates how the abstract software demands of Silicon Valley are directly pulling levers in heavy industrial manufacturing in India.
Completely.
So the power makes it through the main transformers. From there, it goes through switchgear, which routes the electricity. Then it passes through immense uninterruptible power supply, or UPS systems.
Which are essentially rooms full of lithium-ion batteries designed to bridge the gap for a few milliseconds if the grid fails, giving the backup diesel generators time to spin up.
Right. After the UPS, it hits power distribution units on the data floor and finally travels to the server racks.
And it travels there through copper cables.
The cabling section of the report absolutely blew my mind. When you think of cutting-edge AI, you don't immediately think about miles of old-school copper wire.
No, people think it's wireless.
But a 100-megawatt facility requires hundreds of kilometers of thick, highly conductive copper cable. The cabling bill alone is $20 million to $30 million for a single facility.
And here's the economic reality of cable. You cannot recycle it from old facilities. When you build a new AI data center, you need a completely fresh installation.
Because the layouts are different.
Exactly. Furthermore, there is no software efficiency gain that magically reduces the amount of physical cable you need to connect point A to point B.
You can't code around the distance.
Right. The demand for power cable scales perfectly linearly with the physical size of the facility.
And because copper is incredibly dense and heavy relative to its value, the freight costs to ship it across oceans are exorbitant.
You don't want to fly copper around the world.
No.
Yeah.
That creates a massive structural advantage for domestic cable manufacturers serving the local Indian data center build-out. You don't want to import heavy copper cable from China if you can buy it locally. The report explicitly lists 4 Indian companies cashing in heavily on this: Polycab, Finolex Cables, RR Cable, and KEI Industries. Polycab alone posted over 22,000 crore rupees in revenue in FY25, driven in part by this insatiable infrastructure demand.
So that covers layer 1 and layer 2. The power has finally been generated, stepped down from extreme voltages, conditioned by batteries to ensure absolute stability, and delivered via hundreds of miles of copper cable directly to the server rack.
Which brings us to layer 3, compute. We finally get to the actual AI server.
This is where the mathematical magic happens, but it's also where the terrifying thermal reality of physics rears its head.
Inside the heavy metal rack sits the AI server node. A single modern node typically holds 8 highly advanced GPUs paired with 2 CPUs to handle the basic logic. And these servers are incredibly dense. One of these 8 GPU servers costs between $300,000 and $400,000.
Over $1/3 for one metal box the size of a suitcase.
And a 100-megawatt facility holds about 15,000 of these servers. If you do the math, that is roughly 80,000 GPUs, the total hardware cost. $1.5 billion to $2 billion worth of silicon just sitting in those racks.
But the GPUs are useless on their own. And this is where the report dives into a critical engineering constraint known as the memory wall.
Okay, let's explore the memory wall because the physics here are fascinating. If the GPU is the stadium full of workers doing arithmetic, the memory is the workbench where they keep the numbers they are currently adding up.
That's right. And for artificial intelligence, standard computer memory just doesn't work.
Why not?
The neural network models are so massive, containing hundreds of billions of parameters, that the data needs to be fed into the GPU at an astonishing rate. If the GPU finishes its calculation and has to wait even a microsecond for the next batch of data to arrive from memory, the GPU is sitting idle.
And an idle GPU is a massive waste of capital and power. In a normal laptop, the memory chips sit on the motherboard, maybe 3 or 4 centimeters away from the processor.
But the report explains that in an AI server, 3 centimeters is an absolute eternity.
Because of the speed of light?
Strictly because of the speed of light.
Let's do the math on that. This is where electrical engineering collides with fundamental physics. The speed of light in a vacuum is roughly 30 centimeters per nanosecond.
Okay.
Electrical signals and copper traces on a motherboard travel a bit slower than that. A modern GPU operates at a clock speed of around 3 gigahertz, meaning it performs an operation every 0.33 nanoseconds.
Right, very fast.
In 0.33 nanoseconds, light barely travels 10 centimeters. So if the memory is 5 centimeters away, the signal has to travel there and back which takes longer than a single clock cycle of the processor.
The GPU literally calculates faster than the speed of light can deliver the data.
It's blowing my mind. The physical distance the electron has to travel becomes the ultimate bottleneck.
You cannot change the speed of light. So what is the engineering solution? You have to move the memory closer.
Which brings us to high bandwidth memory, or HBM.
HBM represents a massive leap in packaging technology. Instead of placing the memory chips next to the processor on the motherboard, they physically stacks the memory dies directly on top of each other.
Like a skyscraper.
Exactly. And then they place that entire stack on the same silicon interposer as the GPU logic die. The physical distance between the processor and the memory is reduced to less than 5 millimeters.
5 millimeters. And they connect them using microscopic vertical tunnels drilled straight through the silicon, right?
Yes, they are called through-silicon vias, or TSVs. They drill thousands of microscopic holes through the silicon memory chips, fill them with copper, and stack them so the data can flow vertically directly into the processor.
The level of microscopic precision required to align thousands of copper-filled vias across multiple fragile silicon chips is mind-bending.
It really is.
And this extreme precision leads directly to the ultimate upstream choke points of the entire AI revolution. The report makes it clear it doesn't matter how much money Microsoft or Google has. Every advanced AI chip traces back to two specific buildings on planet Earth.
It is the most concentrated supply chain in human history.
One building is in Veldhoven in the Netherlands. The other is in Hsinchu, Taiwan.
Let's start with the Netherlands, ASML.
Right, ASML.
ASML is currently the only company in the world capable of manufacturing the extreme ultraviolet, or EUV, lithography machines. These are the machines required to print the microscopic, nanometer-scale transistors on these advanced chips.
The report says these machines cost over $200 million each, and they only make about 50 to 60 of them a year. Why is there no competitor? Why can't a competitor just build a similar machine?
Because the physics of EUV lithography sound like science fiction. To print features that are just a few nanometers wide, you need light with a remarkably short wavelength.
Okay.
ASML uses 13.5 nanometer EUV light. This light does not exist naturally on Earth. To create it, the machine fires a high-powered laser at microscopic droplets of molten tin falling through a vacuum chamber.
Wait, it shoots falling molten tin with a laser?
It actually shoots each droplet twice. The first laser pulse flattens the droplet into a pancake shape to increase its surface area.
Okay, a tin pancake.
A fraction of a microsecond later, a second, vastly more powerful laser pulse strikes the flattened tin, vaporizing it into a plasma. That plasma emits the 13.5 nanometer EUV light.
That is absurd.
It gets crazier. EUV light is absorbed by absolutely everything, including air.
So it has to be in a vacuum.
The entire process happens in a near-perfect vacuum. Furthermore, you can't focus EUV light with glass lenses because the glass absorbs the light.
So how do they aim it?
You have to bounce it off perfectly smooth, multi-layered mirrors. These mirrors, made by Zeiss in Germany, are so flawlessly polished that if you expanded one to the size of the Earth, the tallest mountain on the surface would be less than a millimeter high.
That level of perfection is hard to even imagine. So ASML has a total monopoly on creating the machines that print the chips, but they don't actually make the chips.
No, they just make the printers.
That brings us to the building in Taiwan, TSMC, the Taiwan Semiconductor Manufacturing Company.
Right. TSMC buys the machines from ASML, and they actually manufacture the silicon wafers for NVIDIA, AMD, and everyone else. But their real choke point in the AI era is the packaging.
Packaging, you mean putting the chip in a plastic box?
No, advanced semiconductor packaging. Specifically, a process TSMC developed called CoWoS, chip-on-wafer-on-substrate.
Okay, what does that actually mean?
This is the proprietary manufacturing process required to take that GPU logic die and meticulously assemble the stacked high-bandwidth memory right next to it, aligning those microscopic 5mm connections with perfect precision.
So if ASML can't produce enough EUV machines or TSMC doesn't have enough CoWoS packaging capacity, the entire global AI build-out grinds to a halt.
Regardless of how many data centers are under construction.
Exactly. The global AI roadmap is held hostage by the manufacturing yield of microscopic droplets of 10 and 5mm silicon stacks.
It's fragile.
Very. Assuming you successfully navigate that choke point, you get the chips, you install them in your multi-billion-dollar data center, and you flip the power switch. What happens next brings us to layer 4, cooling.
Yeah, cooling. When you push 100 megawatts of electricity into silicon chips, the physical process of computation converts that electrical energy into logic, and the unavoidable thermodynamic byproduct is heat. Massive amounts of heat.
A modern NVIDIA chip operates fundamentally like a tiny, incredibly powerful electric heater.
Yes. And the data center industry is going through a massive architectural shift right now because of this.
Historically, data centers relied on air cooling, right? You use powerful fans to blow cold air through the front of the server racks, the hot air exhausts out the back, and large computer room air handler, or CRA units, suck in that hot air and cool it back down using chilled water coils.
That works fine when you are running traditional CPUs that generate maybe 10 to 15 kilowatts of heat per rack. But the report says air cooling has hit an absolute physical wall. Air is simply not dense enough to carry away the heat fast enough. The specific heat capacity of air is too low.
So you can't blow enough of it.
Modern AI server racks packed with GPUs are pushing 100 kilowatts or more. If you try to cool a 100 kilowatt rack with air, you literally cannot move the air fast enough through the narrow gaps in the servers.
It would just get stuck.
It would sound like a jet engine and the chips would still melt.
So you have to use liquid. Specifically, a technology called direct-to-chip liquid cooling, or DLC.
Liquid, specifically water mixed with glycol, has roughly 3,000 times more volumetric heat capacity than air. It can absorb heat much faster and carry it away much more efficiently.
The schematic in the report for DLC is fascinating. They don't just run pipes near the servers, they literally mount a highly engineered metal cold plate directly onto the bare silicon die of the GPU.
Exactly. The water glycol coolant flows through microchannels inside that cold plate, absorbing the heat directly at the source. That warm liquid then flows out of the server to a coolant distribution unit, which uses a heat exchanger to transfer the thermal energy to a massive facility water loop. Finally, that facility water is pumped outside the building to enormous dry coolers or cooling towers to reject the heat into the atmosphere.
We're essentially building multi-billion-dollar liquid-cooled fortresses just to keep these tiny silicon squares from spontaneously combusting.
Pretty much.
And the mechanics of heat exchange are creating massive opportunities for specialized hardware manufacturers.
The report highlights KRN Heat Exchangers, an Indian manufacturer. They specialize in the highly complex aluminum and copper thin-and-tube heat exchangers used inside these cooling systems.
Why are those specific heat exchangers so important?
Because the efficiency of heat transfer depends entirely on surface area and thermal conductivity. Copper has excellent thermal conductivity.
Makes sense.
You run the hot liquid through thin copper tubes, and you attach thousands of tightly spaced aluminum fins to the outside of those tubes.
So the heat spreads out.
Right. The heat conducts from the liquid through the copper into the aluminum fins, and giant fans blow outside air across the fins to whisk the heat away. KRN understands the thermodynamics of creating turbulent flow inside the tubes to maximize heat transfer.
And it's paying off for them. Their revenue exposure to the data center sector has gone from 7% to 15% in a single year, and they are aggressively targeting a 50% market share in India.
So that's layer 4.
Okay, so the chips are powered by massive substations. They are liquid-cooled by intricate heat exchangers. The GPUs are calculating away, but a single chip, or even a single rack of 8 GPUs, is completely useless for training a frontier model with hundreds of billions of parameters.
They have to act as a unified collective.
And that brings us to the final and often most underappreciated layer of the data center infrastructure, layer 5, networking and connectivity.
This is the central nervous system. It's a high-speed fabric that links tens of thousands of individual GPUs together so they can behave as a single, massive, unified brain.
The report notes that networking represents 10 to 15% of the total IT capital expenditure. Why is the network just as critical as the compute?
Well, imagine you have 100,000 GPUs working on a single, massive matrix multiplication. They take a huge mathematical problem, break it into tiny pieces, and hand one piece to each GPU.
Okay.
But to finish the calculation, they must constantly share their intermediate results with each other. If the networking fabric is slow, or if it drops packets of data, one GPU finishes its math and has to wait for data to arrive from another GPU on the other side of the building.
And as we established earlier, an idle GPU is a massive waste of power and money.
Exactly. If one GPU stalls waiting for data, thousands of other GPUs might hit a cascading stall waiting for that first one. The network has to be perfectly synchronized with nearly zero latency across massive distances inside the data center.
I look at it like the human brain. If the GPUs are the muscle tissue doing the heavy lifting, the optical networking transceivers are the synapses connecting the neurons. Without the synapses firing instantly, the muscles cannot coordinate complex movements.
That is a great analogy.
Mm.
And the sheer physical volume of these synapses required is a hidden story that most investors completely miss.
Mm.
You don't use regular copper Ethernet cables to connect 100,000 GPUs. The data rate is too high.
So what do you use?
You use fiber optic cables, which transmit data using pulses of light.
But the GPU generates an electrical signal, so you need something to translate electricity into light.
Yes, every single connection between a server and a network switch requires an optical transceiver. It is a highly complex optoelectronic module, roughly the size of a pack of chewing gum.
It's a little pack.
Yeah, it takes the electrical signal from the GPU, uses a microscopic laser to convert it into incredibly fast pulses of light, sends it down the fiber optic cable, and then a photodetector on the other end converts the light back into an electrical signal.
A pack of chewing gum with lasers inside, and how many of these do they actually need for a large facility?
For a 100,000 GPU cluster, because of the complex, redundant web of connections required, you need anywhere from 100,000 to 300,000 of these optical transceivers.
Hundreds of thousands of them. At $50 to $200 each, depending on the speed, you are looking at $30 million to $50 million spent strictly on these little laser gum packs per facility.
And just like the memory wall we discussed earlier, the network is hitting a profound physical wall as well. The power required to push the high-speed electrical signal from the GPU chip across the circuit board out to the pluggable transceiver on the front panel of this server is becoming astronomically high.
The signal degrades.
Right. At 800 gigabit, or 1.6 terabit speeds, the electrical signal degrades incredibly quickly over even a few inches of copper trace.
So if the problem is the electrical signal traveling a few inches across the board, the solution must be exactly what they did with the HBM memory: shrink the distance.
Precisely. The industry is currently undergoing a massive technology transition toward co-packaged optics, or CPO.
Co-packaged optics.
Instead of having a pluggable optical transceiver sitting on the edge of the board tens of centimeters away, they are moving the optical engine directly onto the same semiconductor package as the network switch chip itself.
They are bringing the laser right next to the silicon switch. They are shrinking the distance the electrical signal has to travel from tens of centimeters down to tens of millimeters.
By doing that, you drastically reduce the power required to drive the signal, and you significantly increase the total bandwidth density. NVIDIA has already announced their first CPO network switches.
So it's already happening.
It will take years for the industry to fully transition from pluggable transceivers to co-packaged optics, but it represents a structural shift for companies supplying fiber and networking hardware.
The report mentions Indian firms like HFCL and Sterlite Technologies pivoting hard to supply the high-density fiber required for these new architectures.
Yeah, the demand for fiber is going to be massive.
Okay, so we have conceptually built the ultimate data center. We generated the power, stepped it down, cooled the racks, computed the math, and networked the GPUs with lasers. But the report includes a fascinating framework called the constraint hierarchy.
The constraint hierarchy is vital because a data center is an interdependent system.
Right, all the layers depend on each other.
Exactly. A bottleneck in any single layer constrains the entire facility.
Yeah.
You cannot utilize more GPUs than you can network. You cannot cool more racks than you can reliably power.
So what is the ultimate limiting factor? What sets the pace for everything else?
The ultimate pace is dictated entirely by lead times. Let's work backwards. Securing networking equipment and optical transceivers takes roughly 3 to 9 months.
Okay, not too bad.
Procuring advanced liquid cooling CDUs takes 6 to 12 months. Ordering the custom high-voltage transformers, as we discussed, takes 12 to 24 months, often longer now.
Right, the artisanal steel transformer.
Ordering the massive combined-cycle gas turbines takes 24 to 60 months.
So you are planning facilities 5 years in advance.
Yes, but the ultimate bottleneck, the absolute top of the hierarchy, is grid interconnection.
Getting permission from the local utility to tap into the public grid.
Getting the permits, conducting the environmental studies, upgrading the regional transmission lines, and physically pulling 100 megawatts from a public power grid can take anywhere from 36 to 84 months.
84 months. 7 full years just to get the electricity turned on.
It's the biggest roadblock.
No wonder companies like Microsoft and Amazon are pouring billions into natural gas and solar, and even looking at small modular nuclear reactors. They physically cannot wait 7 years for the grid to catch up to the software.
They cannot afford the delay, which leads directly to Section 7 and perhaps the most brutal financial reality of this entire infrastructure boom: depreciation cycles.
This part was wild.
Let's say you manage to secure the land,
navigate the 84 months grid wait, buy the transformers, and stand up this $3.5 billion facility. How long does the equipment actually last before it becomes obsolete?
I was absolutely stunned by this section. You spent all this capital. How long is it actually useful?
The report quotes a former senior executive at a major chip design firm. They explained that technically, the physical server hardware, the motherboard, the chassis, the power supplies, can reliably run for 5 or 6 years.
Like a normal computer.
But commercially,
Yeah.
economically, the AI hardware refresh cycle is so incredibly intense that on the balance sheet, training servers are effectively obsolete in 2 to 3 years.
2 to 3 years, that is insane.
Let's walk through the financial logic. Let's say you buy 10,000 GPUs today. 2 years from now, NVIDIA releases a new architecture that is 3 times faster and twice as power efficient.
Which is exactly what happened going from the A100 to the H100 and now to the Blackwell architecture.
Right. Now you have a physical building that only has a strict 100 megawatts of power available. That power is your absolute hard limit. Does it make economic sense to use your precious 100 megawatts to power 10,000 old, slow chips? Or does it make more sense to rep them out, throw them away, and use that same 100 megawatts to power new chips that can train a vastly superior AI model in a third of the time?
Oh, I see. The constraint isn't the physical life of the metal box. The constraint is the power envelope of the building. Because power is scarce, you have to maximize the amount of computation you squeeze out of every single megawatt. If the new chips are more efficient, you have to upgrade.
Exactly. It becomes economically irrational to keep training on old silicon. The space and power they consume is more valuable than the hardware itself.
Wow.
For inference servers, the life cycle is slightly longer, perhaps 3 to 5 years, because inference tasks are less demanding. But for training frontier models, it is a continuous cycle of violent capital destruction and renewal.
You spend $3 billion, and 36 months later, you have to rip out the entire silicon heart of the facility and start over just to stay competitive. It is a treadmill that never stops.
And as the technology matures, the architecture of where these facilities are built is also about to change radically. The report details a forthcoming structural shift in the ratio between training and inference compute.
Right now, the vast majority of compute, roughly 70%, is dedicated to training the models. It is the R&D phase. And only 30% is dedicated to inference, which is users querying the models.
But the source predicts that within a few years, as AI becomes deeply embedded in every enterprise application, every smartphone, and every autonomous vehicle, that ratio will flip. It will eventually settle at roughly 30% training and 70% inference.
Why does that flip dictate where the data centers are built?
Because of latency. As we discussed, training runs happen over weeks or months. It doesn't matter if the training facility is located in a remote desert, hundreds of miles from a major city, as long as the power is cheap. But inference requires extreme low latency.
Latency meaning the time it takes for the signal to travel from the user to the server and back.
Yes. When you ask your digital assistant a question, or a doctor's AI analyzes a live ultrasound, or an autonomous car makes a routing decision, you need a near instantaneous response. You physically cannot wait for the fiber optic signal to travel to a remote mega campus in the desert and back.
Because the speed of light introduces too much delay.
Right, the speed of light strikes again, so the compute has to be physically close to the end user. The report predicts a massive proliferation of smaller, highly dense edge sites. Instead of just building 100-megawatt campuses in the middle of nowhere, companies will need to build 5 to 10 megawatt edge data centers located every 30 to 50 kilometers in major metropolitan areas globally.
So this infrastructure build-out isn't just a handful of massive remote fortresses. It is going to be a compounding, continuous geographic expansion directly into our cities and our suburbs.
And every single one of those hundreds of edge sites will need dedicated transformers, redundant switchgear, direct-to-chip liquid cooling systems, thousands of optical transceivers, and miles upon miles of copper cable. The AI infrastructure opportunity is not a one-off event. It is a permanent structural shift in how we build and deploy global industrial infrastructure.
Okay, let's take a breath and zoom out. We have covered an immense amount of ground today.
We really have.
We started at the ethereal software promise of ChatGPT and mRNA vaccines, and we dug all the way down to a 100-megawatt connection to the high-voltage grid. We explored the physics of transformers and grain-oriented steel. We went down to a 5-millimeter gap between a GPU and its memory block, and we looked at how lasers convert electrical signals into light.
It really paints a comprehensive picture of the reality behind the hype. The next time you read a headline about a massive new AI breakthrough, I want you to immediately think of the heavy industry, the cooling loops, the tin droplets, and the copper cables, making it physically possible.
It totally changes your perspective. But pulling all of this together leaves me with a deeply provocative thought. For the last 20 years, technology was dominated by software. It was a world of pure code, infinite scalability, and zero marginal costs. Silicon Valley ruled the world because they controlled the code, and code was weightless.
Yes, the era of the ethereal cloud.
But the AI era has abruptly and violently dragged technology back into the physical world. Think about what we've established today. The future of global intelligence, the actual physical limit on how smart our AI can get, is no longer strictly gated by software talent. It is gated by the physical availability of copper wire, grain-oriented electrical steel, heavy transformer manufacturing, and access to massive amounts of industrial cooling water and electricity.
It is a profound geopolitical and economic question. If intelligence is constrained by physical materials, does the balance of global power shift away from the software coder sitting in Silicon Valley and back toward the nations, the regions, and the specific heavy industrial companies that control energy generation, physical manufacturing, and the raw materials?
It is entirely possible that the most important tech companies of the next decade won't be software companies at all. They will be the companies that can forge the steel and cool the silicon. It is something to seriously mull over. The cloud is made of steel, copper, and water now. Thank you so much for joining us on this deep dive. The next time you are walking around your neighborhood and you see those thick power lines overhead, or you hear the low hum radiating from a green transformer box on the corner, I guarantee you are going to look at them with a completely new perspective. Until next time.